Hi, my name is Kristen. Welcome to this journey through digital product design and 3D printing. Today, we are going to study the chapter, which is Design for 3D Printing. In this chapter, we'll learn how to prepare digital models for optimal 3D printing. You'll see how aspects like tolerances, overhangs, wall thickness, and part fitment directly affect print quality. These are essential considerations for making functional, efficient, and reliable parts. Let's get started. 2. What is Design for 3D Printing? Design for 3D printing means preparing a CAD model while considering printer limitations and material behavior. It ensures that what you model on screen can actually be printed well in the physical world. Without thoughtful design, prints may warp, fail, or not function as intended. It's the missing link between CAD modeling and successful manufacturing. 3. Tolerances. Why they matter. Tolerances refer to the intentional gaps between parts that need to fit together. Since 3D prints can swell slightly or have layer inconsistencies, parts with no clearance may jam. A common practice is to allow 0.2 to 0.5 millimeters of space between mating parts. Without proper tolerance, assemblies often fail. 4. Tolerances. Design guidelines. Different materials and printers behave differently, so tolerance testing is crucial. In most FDM prints, a 0.3 millimeter clearance allows for a smooth fit. Use CAD tools like Fusion 360 to assign fit types. Always prototype key assemblies in small scale to confirm fit before committing to the full print. 5. Wall thickness. Introduction. Wall thickness controls the strength and printability of your model. Thin walls may result in fragile or broken parts, while overly thick ones waste filament and time. Design must strike a balance between function, print time, and material usage. Let's see how to find that sweet spot. 6. Wall thickness. Best practices. Wall thickness should be a multiple of your nozzle size. For a 0.4 mm nozzle, the minimum recommended wall thickness is 0.8 mm. For durable parts, 1.2 mm is standard. Use slicer previews to detect thin areas. Stronger materials can go thinner, but testing is always advised. 7. Overhangs. Understanding the challenge. Overhangs occur when the printer tries to print in mid-air without enough support. FDM printers struggle with angles over 45 degrees. This can cause sagging, stringing, or total failure. Designing with support in mind saves time and improves surface quality. 8. Overhangs and bridging. Design solutions. For best results, design overhangs under 45 degrees. Use chamfers or split parts. Bridges, horizontal gaps, can span small distances if short and cooled quickly. Use slicer simulation to preview problem areas. Orientation can often reduce the need for support altogether. 9. Assembly fitment. Overview. Parts that must fit together after printing need precise design. Too tight, and you'll need sanding. Too loose, and you'll get a shaky fit. Thoughtful use of tolerances and guides ensures smooth assembly without post-processing. It's a critical skill in functional 3D design. 10. Assembly fitment. Smart design. Leave. 0.3 and 0.6 mm clearance between mating parts. Add alignment features like pegs and tabs for easier assembly. Consider thermal shrinkage in ABS or nylon. Use your CAD-D tool to simulate fit before exporting. Test prints are always helpful before a final build. 11. Moving parts in one print. Introduction. 3D printing allows you to design entire mechanisms, like hinges or gears, in one go. This is known as print-in-place design. Success depends on clearance, geometry, and avoiding fusing. Let's look at how to make it work reliably. 12. Print in place. How to achieve it. To enable motion, keep a gap of 0.4–0.6 mm between parts. Curved or slanted separation surfaces reduce fusion. Avoid completely flat contact surfaces. Slice visually, and check layer paths before printing. Print-in-place designs show the true potential of additive manufacturing. 13. Hollow structures. The concept. Solid parts take longer to print and consume more material. Hollow structures help reduce weight and cost, especially for aesthetic or non-load-bearing parts. Most slicers use infill to create internal hollowness, but you can also model hollow cavities directly. 14. Hollow structures. Design advice. Use 2–3 lithnose outer walls and 20–30% infill for strength. Consider gyroid or honeycomb patterns for structural efficiency. Add escape holes for SLA prints to drain resin. Lightweight prints are faster and cheaper, smart for prototyping and drones. 15. Print strength. Overview. Parts may look perfect, but fail under stress if not designed properly. Strength in 3D prints depends on wall count, layer bonding, material choice, and orientation. FDM prints are weaker along the Z-axis. Knowing how to orient your model is key. 16. Strength optimization. Tips. Align stress paths along layer lines. Use 3–4 walls for stronger parts. Choose infill patterns like cubic or grid for even force distribution. Add fillets instead of sharp corners to reduce stress concentration. For load-bearing parts, consider PETG or carbon-reinforced filaments. 17. Case study. Gearbox assembly. A gear system was designed with 0.4 mm clearances and printed as a single unit. The designer used curved interfaces and optimized overhangs to avoid support. With 1.2 mm walls and 25% infill, the part turned smoothly post-print. It required no assembly or sanding. 18. Case study, drone frame. This drone frame used hollow tubes, printed with gyroid infill, and 2 mm thick walls. It was designed to absorb impact with flexible geometry. Orientation was chosen to reduce Z-layer splits. The print was lightweight, crash-resistant, and ready to fly. 19. Summary of design principles. Here's a quick recap. Use tolerances between 0.2–0.6 mm. Maintain 0.8–1.2 mm wall thickness. Limit overhangs to 45 degrees or support them. Design assemblies and moving parts with clearances. Hollow structures and strength-oriented orientation reduce cost and failure. 20. Closing thoughts. Designing for 3D printing bridges theory and practice. Every decision, fit, thickness, support, material, affects the final output. As engineers, our role is to design smart, test quickly, and iterate fast. 3D printing gives us that freedom. Keep experimenting. And remember, good design begins before you even hit print.